I'm Jeroen and welcome to my lecture series on computer and network security. In the previous video, I showed how certificates can be used to securely exchange public keys without a central authority being involved in the actual key exchange. In this fifth and last video on key distribution, I will introduce the X.509 standard, which is the most commonly used standard for public key certificates on the Internet. The ITU X509 recommendation is part of the X500 series of recommendations that define a directory service. This in effect is a server or distributed set of servers that maintains a database of information about users. An X509 defines the framework for the provisioning of authentication services by this X500 directory to the users. It can serve as a directory and repository of public key certificates, and each certificate contains the public key of a user and is signed with a private key of a certification authority, trusted by that user. It defines authentication protocols based on the use of public key certificates. It's a very important standard because it's widely used in many networked applications. For example, IP layer security or IPsec, transport layer security or TLS, the email security standard SMIME, and so on. Currently, 7 different versions are available of the X509 recommendation. The first one was standardized in 1988, and the most recent one, version 7, in 2012. In version 3, since version 3, no more changes have been made to the actual format of the certificates, but only new optional features have been added. In this figure, you can see more details about how X509 certificates work. Specifically, the certificate contains a plethora of information, such as the identifier of the owner of the public key that is being certified, and additional information about the certification authority. This information comprises the unsigned certificate. Obviously, this needs to be signed to ensure that no one who doesn't have the proper authorization changes the information. As such, a digital signature is generated and appended to the certificate. This is done much in the same way as I have explained in previous videos. So the information is given as input to a secure hashing algorithm, which creates a fixed length hash value, which is then encrypted with the private key of the certification authority, and this is used as a signature. Recall that validating a signature is quite straightforward, because anyone that receives the certificate with signature can also take the unsigned certificate information, give it as input to the same hashing algorithm, calculate the fixed length hash value, and compare that to the decrypted signature. If they are the same, then the information has been validated and has not been changed by an unauthorized entity. The decryption algorithm obviously uses the public key of the certification authority. No one can then alter the information in the certificate without having access to the private key of the certification authority. So, as long as that private key is secure, we are sure that the certificate has not been tampered with. And here you can see all the information that is embedded into an X509 certificate. The first field is the version. As I mentioned, the version can go from version 1 up to version 7. However, since version 3, no changes have been made to this format. On the right, you can see which versions contain which fields. So version 1 does not contain the information below this point, while version 3 contains everything down to the bottom. Second is the certificate serial number, which is a unique identifier of the certificate. Third is the algorithm that was used to sign the certificate. Note that X509 does not specify which algorithms should be used, so the certificate needs to contain more details about what algorithm to use to verify the signature. For example, RSA can be used, but also other algorithms. Next is the name of the certification authority that created and verified this certificate. Then is the period of validity. When is a certificate valid and when does it expire? The name of the owner of the public key. The public key itself. This is not only the key, but also information about how the key should be used. So for which algorithm it's intended, what are the parameters of this algorithm, and what is the value of the public key. Next, and this was added in version 2 of the standard, is the unique identifier of the certification authority. This allows reuse of the actual plain text name, which is added here. The same for the unique identifier of the owner of the key. Finally, there are some extensions which can be used from version 3 onwards. And obviously at the end, and this is included in all versions, is the signature itself. So this mentions the algorithms used to create a signature, as well as the encrypted hash value that forms the signature itself. In practice, however, a single certificate authority is not sufficient. If the number of users is very large, then multiple certification authorities are needed. This is, for example, the case on the internet. And let us define a certificate based on the user, X, and the certificate authority that issued the certificate, Y. So we can write in this way a certificate issued by Y for user X, his public key. So let's now say two users, A and B, want to obtain each other's public key, but they don't trust the same certificate authority. User A trusts certificate authority X, while user B trusts only Y. However, these certificate authorities can also have trust in one another in a hierarchy of certificates. For example, X could own a certificate to the public key of Y, and Y could own one for the public key of X. So these two authorities now trust each other. Since A owns a certificate issued by X for its own public key and B owns one issued by Y, A can validate the validity of B's public key by creating a chain of certificates. Because A trusts X, X trusts Y, and Y trusts B, and therefore, since we trust X and X trusts Y, we trust in the certificate issued by Y. And this doesn't have to be limited to two certification authorities. A tree of authorities can be created. And this allows us to create an arbitrary long chain of certificates to validate a key. In this example, C has a public key certificate issued by X, and C only trusts in X. But if C trusts X, then it can get a trusted certificate for B's public key. Because C trusts X, X trusts W, W trusts V, V trusts Y, Y trusts Z, and Z trusts B. And this creates a chain, as you can see here, of certificates to denote trusts within this hierarchical organization. And within this hierarchical structure, two types of certificates are stored by every certification authority. The first one are forward certificates. These are certificates generated by other certification authorities of X that show X to trust these certification authorities. The reverse certificates are certificates X has generated of other certification authorities. And by using these two types of certificates, a chain can always be created throughout this tree, a chain of trust. And even if certificates have an expiration date after which they are no longer valid, it may be needed to revoke them even if they have not yet expired. For example, if the user's private key is compromised, the user will need to also change his public key. If the user is no longer being certified by the certification authority, or if the certificate has been compromised because, for example, the private key of the certification authority is no longer secure. So whenever a user obtains a certificate, they should check if that certificate has not been added to the revocation list of the signing certification authority. And this revocation list contains different types of information. It contains all the certificates that have been revoked but have not yet expired. So here's the list of these revoked certificates. It also contains information about when the list was last updated and when it will next be updated, so that a user that downloads the list doesn't need to re-download it every time it wants to check a certificate, but only when this next update time is reached. And from version 3 onwards, the X.509 certificate structure also contains some extension fields. These fields add additional information about the certificate, the keys, the subject or the issuer. And they contain three types of information. The first is information about the keys themselves. This, for example, allows the certification authority or the user to define a unique identifier for their key, which then allows them to have multiple keys and multiple certificates for these different keys. It also allows them to restrict what the key can be used for. For example, can the public key be used for a key exchange, for encryption, and so on. Second type of information is the information about the subject and the issuer. For example, it allows to define an alias for the user or the certification authority. Third is information about the certificate path. This is useful when used in a hierarchy of certification authorities. For example, it allows defining whether or not the subject, so the one that owns the public key, is allowed to act as a certification authority themselves, and so on. And in addition to the X.509 recommendation, which defines the structure of the certificates themselves, there is also the IETF request for comments, or RFC 4949, which defines a public key infrastructure, which makes use of these certificates to define an architecture to be deployed on the internet to handle all aspects related to public key distribution. So it is a set of hardware, software, people, policies, and procedures needed to create, manage, store, distribute, and revoke digital certificates based on asymmetric cryptography. The objectives are to enable secure, convenient, and efficient acquisition of public keys. And here you see an overview of the public key infrastructure X.509 or PKIX architectural model with communication between all involved entities. And the entities can be split into two main types. First are the management entities, second are the users. The main management entity is obviously the certificate authority. This certificate authority, however, communicates with some other entities involved in public key management. First, it can exchange information with other certificate authorities for cross-certification. Then there are two optional entities which have been added to the architectural model. There is the registration authority, which is an optional entity that takes over some of the responsibilities of the certification authority, such as the publication of certificates. These certificates are then published into a distributed repository of certificates that can be accessed by the users. The second optional entity is the CRL, which takes over revocation tasks from the certification authority. So the CRL issuer will publish the revocation list of the certificates. Also, this one is published to a distributed repository that can be accessed by the end users. The end users will communicate with certification authorities and registration authorities to register new public key certificates, to recover key pairs, to update them, and to send revocation requests. And the PKIX provides a lot of different management functionalities. These functions can be provided by two alternative protocols, and the user can select one of them. They are CMP and CMC, both defined in separate RFCs. Here you can also see a list of the different functions that the public key infrastructure provides. They are registration, where users make themselves known to the certification authority and exchange a shared secret key. Initialization, where the public and private keys are initialized. Certification, where the certification authority issues a certificate for the user's public key and posts it for others to retrieve. Key pair recovery, where decryption keys can be recovered when keying material is not available. Key pair update, where the key can be replaced and certificates can be updated for extra security. Revocation requests, where the user asks to revoke the certificate of their public key when abnormal behavior is detected. And cross-certification, where two certification authorities exchange information and mutual certificates for use in a certification hierarchy. And this ends my video on public key infrastructure and certificates, and also ends my video series on key distribution. Thank you for watching.